For decades, astronomers have studied the death sequence of stars. Stars like our Sun have a death process that lasts a few billion years. However, there are massive stars, stars with a size 10 times or more than our own Sun, that will supernova and shine for a few days or up to a few months. The final outcome from this is usually an extremely dense and compact remnant, a neutron star or a black hole. This process is a cornerstone of astrophysics and largely explains the distribution of heavy elements in the universe. So what happens when astronomers encounter a star that disregards everything we thought we knew about this stage? Welcome to Astroracle, where we explore the vast universe together. In the Andromeda galaxy, about 2.5 million light-years away, a massive star known as M31 2014 DS1 vanished without producing the expected supernova explosion. How is this possible? What explanation could there be for this? Observations began in 2014 when M31 2014 DS1 showed an increase in brightness in the mid-infrared range. For approximately 1,000 days, this increase remained stable. Then, over a similar period of time between 2016 and 2019, the star's brightness noticeably began to fade. Fast forward to 2023, telescopes conducting deep observations in optical light and near-infrared found no trace of the star. What had once been a bright, perfectly identifiable point in Andromeda's catalogs had vanished. The first hypothesis could have been that it was a variable star, one whose brightness, as seen from Earth, changes with time. But the recorded fluctuations did not match this typical behavior of such objects. According to the research team led by Kishley Day from the Kavli Institute for Astrophysics and the Massachusetts Institute of Technology, the star had been born with an initial mass of roughly 20 times that of our Sun, and had reached its final stage with about 6.7 solar masses. Everything indicated it was the last stage of its life, a stage that, according to models, should end in a core collapse supernova. These supernovae, known as Type II, are rare in our galaxy, occurring roughly every 100 years. They possess great scientific interest because they not only mark the end of a star, but also release enormous amounts of energy, produce heavy elements like iron, and their shock waves can trigger the formation of new celestial bodies. However, the case of M31 2014 DS1 suggested that not all massive stars follow these rules. The collected data showed that the star was shrouded in a layer of dust, expelled shortly before its disappearance. This could be something associated with an explosion, but there was no optical signal confirming that such an explosion had occurred. All evidence pointed to a failed supernova, a direct collapse into a black hole without a visible explosion. This type of phenomenon, while theoretically possible, is extremely difficult to confirm because its main feature is the absence of a luminous event to reveal it. The process that normally leads to a supernova includes a critical stage, in which electrons in the core, experiencing extreme pressure and density, combine with protons to form neutrons and neutrinos, a process called neutronization. Neutrinos are subatomic particles with no electric charge and barely interact with matter. Every second of our lives, billions of them pass through our bodies without leaving a trace. However, in the dense interior of a dying star, the concentration of neutrinos is so high that part of their energy can be transferred to the surrounding matter, generating a shockwave. This shock, if successfully reactivated, can expel the outer layers of the star and produce a supernova. If that reactivation does not occur, the wave stalls and the collapse continues until a black hole forms. In M31 2014 DS1, the neutrino-driven shock failed to reactivate. Researchers calculated that the amount of mass ejected was far less than that of a typical supernova, and that around 98% of the star's mass collapsed into the core. This would have formed a black hole of about 6.5 solar masses, leaving virtually nothing to observe from the outside. What had once been a point of light in Andromeda's night sky became completely invisible, detectable only through indirect methods. This is not the only known case of a failed supernova. In 2009, a similar phenomenon was observed in the galaxy NGC 6946, known as the Fireworks Galaxy. There, a red supergiant of about 25 solar masses, cataloged as N6946-BH1, experienced an increase in brightness until it reached roughly 1 million times the sun's luminosity. 6 years later, it had vanished from optical light, leaving only a faint infrared glow. In both cases, the evidence pointed to the star having collapsed directly into a black hole without undergoing a visible explosion phase. The challenge in detecting such events lies in the fact that traditional supernova searches rely on spotting sudden increases in brightness. A failed supernova does not offer that signal. Monitoring programs such as the ones carried out with the Large Binocular Telescope have attempted to track the disappearance of massive stars in nearby galaxies. Among 27 observed galaxies, the results suggest that between 20 and 30% of massive stars could end their lives this way, although direct evidence remains scarce, and for now, only M31 2014 DS1 and N6946 BH1 have solid confirmation. The silent disappearances of a star like M31 2014 DS1 raises important questions. If a significant fraction of massive stars avoid the explosion and collapse directly, this could change our estimates of how many heavy elements are dispersed into the cosmos and therefore influence models of galactic chemical evolution. This could also mean that there is a larger population of black holes formed directly, without luminous violence of a supernova, making them harder to detect and account for. Understanding the conditions that led to a direct collapse without an explosion is a challenge for astrophysicists. Among the hypotheses are differences in the internal structure of the star, variations in chemical composition, interactions with companion stars, or the influence of extreme magnetic fields. The amount of energy generated by neutrinos during the collapse could also play a role, since if it is insufficient, then the shockwave fails to expel the outer layers. The case of M31 2014 DS1 is particularly relevant because it is located in the galaxy closest to ours, allowing for more detailed observations than in more distant systems. However, even with this advantage, the phenomenon is characterized by the lack of visible signals, forcing researchers to rely on the infrared data and the indirect analysis to reconstruct what happened. Next-generation space and ground-based telescopes, along with neutrino detectors and gravitational wave observations, could in the future provide more clues about these events. The confirmation of failed supernovae also has implications for gravitational wave astronomy. The direct formation of a black hole could produce a weak but detectable signal for sensitive instruments, opening a new pathway to study these invisible objects. Moreover, if these silent collapses are more common than we think, it could be contributing to the population of binary black holes that later merge and are detected by LIGO and Virgo. The disappearance of M31 2014 DS1 is not just a curious event, but a direct challenge to our understanding of how massive stars die. For decades, the standard picture has been that of a bright supernova marking the end of a star's life. This case shows that reality is more complex and that, in some instances, a star can skip the most spectacular phase of its death and go straight to becoming a black hole, leaving no luminous trace behind. If you're enjoying the video, give it a like, and subscribe to the channel for more content like this. And don't forget to hit the notification bell so YouTube can let you know when we upload a new video. The universe continues to hold mysteries, even in processes we thought we understood well. Science advances precisely by confronting these expectations, searching the data for clues that might explain why some stars explode in a dazzling display of light, while others simply fade away forever. This case, documented patiently over nearly a decade, will join a very small catalog of confirmed stellar disappearances and will become an essential reference for any future research on failed supernovas.